Okay, thank you very much for introduction. So, good morning, everybody here in Brazil. Good afternoon to all our European colleagues. In my presentation, I would like to speak about phase transition in spin-1 half, Ising-Heisenberg and Heisenberg models on diamond-decorated square lattice in magnetic field. This work has been done in collaboration with Taras Verkoliak, Katarina Karlova, Niels Kaki, Stefan Wessel, and Andreas Honecker. So, this is outline of my talk. After brief introduction, I will focus on two kinds of models. First one is we call it Ising-Heisenberg model. The second one, pure Heisenberg model. And then at the end of my talk, I would like to conclude and my presentation and show you some future outlooks and our further ideas, what can be done and why it's interesting to study these kind of models. So one of the most interesting topics in physics is maybe the concept of phase transition. It's quite unusual, phase transitions, and many quantities of some system which undergo phase transition usually have very unusual behavior, including divergences and other type of singularities. Maybe the best known system which shows phase transition is water. This is maybe textbook example of temperature, pressure, phase diagram of water. As you can see, you can have three kind of phases: solid phase, liquid phase, and gaseous phase of the water. And all these phases are separated by discontinuous first-order phase transition lines, which are shown by these black lines. And what is important, along this line, density of these different phases changes discontinuously. And if we want to change the nature of the substance of the water, we need to add across these lines some latent heat. So we are giving heat, but the temperature is kept constant. So in fact, we see that specific heat is ill-defined because it diverges from that point of view. Among three first-order phase transition line, maybe the most interesting one is the first-order phase transition line between liquid and gaseous form of the water. So this line between the point B and C. Namely, it starts in the triple point when all three phases coexist together, but it ends at some very specific point. And this specific point is called liquid-gas critical point. Why it is so? Because if you change or if you move along this first-order phase transition line, so the difference between densities of liquid and gaseous form of the water is gradually diminishing, and at this point, it in fact terminates. So that we have very special critical point, namely second-order phase transition. So density is continuous for the specific case of phase transition, and no latent heat is needed for that. Okay, so you can see this kind of typical behavior of density as a function of temperature on this picture down. So you see that you can have, for a given temperature, two kind of solution with two different densities. Smaller density, of course, correspond to the vapor, and the greater density to the liquid form of the water. So maybe these two words should be interchanged. And you see that they really terminate at some critical temperature, roughly 374 degrees of Celsius. Something similar is found also in, not only in water, but also in magnetism. And it is quite typical to find such kind of unusual phase transition in magnets. Here is a typical behavior, how the magnetization looks like as a function of temperature. Maybe for us working in magnetism, it's a little bit strange that magnetization on x-axis and temperature on y-axis, but this is just because I would like to make it, just to show the correspondence between this behavior of density difference in water and magnetism. So we see that we have always two branches of the solution, one with negative magnetization and the other one with positive. And if you increase temperature, both solutions are gradually converging to zero value, and at critical temperature, they vanish with some critical exponent beta. And above it, we have some disordered state with zero magnetization, zero spontaneous magnetization, with the same number of spin pointing up and down as schematically shown in this figure. So main point of my talk will be phase transition. That's why this was some introduction. In fact, it's not so easy to study phase transition. So usually we need to solve some model in thermodynamic limits, so infinitely large system. To my knowledge, the first exactly solvable model which shows unusual phase transition was spin-1 Ising model square lattice, studied by Onzager. And this is a typical plot. Now I am just showing this branch with positive solution and in most common way when on x-axis is temperature. And you see that indeed magnetization continuously diminishes, and with close to critical temperature with some power law exponent 1/8. This was really amazing breakthrough when the critical exponent for magnetization was found, because until that time, the people believed a Landau theory of phase transition that all this behavior should be governed by mean field like critical exponent, and for magnetization should be 1/2. So this is something what is called classical phase transition. But there is also another option to have quantum phase transition, which appears at zero temperature, and it is not driven by the temperature fluctuation. If you increase temperature in this square lattice Ising model and you start from some ferromagnetic ground state, you are just flipping few spins with some Boltzmann way, and the higher is the temperature, the greater chance is that the greater number of spins are flipped, and that's why magnetization decreases. But similar effect can be achieved, for instance, if you take one-dimensional Ising chain in so-called transverse magnetic field, when we apply field perpendicular to the spin z projection of spins, if we leave to interact just z component of the spins. And if you would solve this model, as was solved by Felty in 70, so one will find something very similar. Magnetization continuously decreases with the magnitude of the transverse field, and around some critical field, it is also showing second order continuous phase transition. And what is also quite interesting, of the same university class like 2D Ising model, this is not only accident, this is because both models, they are somehow connected, as was shown that one-dimensional quantum Ising model is in fact equivalent in a non-zero transverse field, can be shown to be equivalent to two-dimensional Ising model in zero field. So then one can show some correspondence as was shown by Lieb, Schultz, and Mattis. Okay, this is not main subject what I would like to speak about. Namely, Ising models are not really good for real magnetic substances. The reason is that the spin is isotropic property in real space. Spin doesn't have some preferred projection, and most of the compounds, magnetic substances, are from the family of magnetic insulators, are well modeled by quantum Heisenberg model given by this Hamiltonian, which contains scalar product between spin operators. So let me focus on this model from the point of view of phase transition. So what we know rigorously about that, Mermin-Wagner theorem says that this kind of model cannot have classical, so finite temperature phase transition for any 1D or two-dimensional Heisenberg models, for any 1D or two-dimensional lattices. So one would say that it is quite boring from that point of view, and one would need to consider three-dimensional Heisenberg model in order to study phase transition. On the other hand, if we apply a non-zero external field, so in that case, the Mermin-Wagner theorem doesn't apply. And this kind of model can have very rich phase transition. Namely, it can have field-driven quantum phase transition due to magnetic field, and it doesn't matter whether it's transverse or longitudinal, even at zero temperature, or it can have also classical phase transition, and it can appear even for 1D and 2D models. So this kind of model is really rich, and it shows zoo of quantum phases and phase transition. So before I finish my introductory remarks, I will just on one slide mention some experimental connection. To be honest, we don't have a real magnetic system which would be modeled by the models which I will present hereafter, but its basic unit cell is found in many magnetic compounds. We have a lot of examples of so-called Heisenberg diamond chain. Maybe the best known example is azurite, this natural mineral shown in this figure, and here is shown part of its crystal structure. Blue circles denote lattice position of copper 2+ ion, which are spin-1 particles, and its magnetic structure. That's why it corresponds to the diamond chain. So you see that the elementary unit is a diamond chain. This is how the typical magnetization curve of azurite looks like. So it shows some interesting 1/3 magnetization plateau and continuous rises around zero field up to lower edge of 1/3 plateau and between upper edge of 1/3 plateau and saturation. There are a lot of other examples of diamond chains. For instance, these 5 analogs were prepared by Fujita et al. And this is one of them, crystal structure. They were not studied so well like azurite, so there are not so many magnetic measurements for them. But also interesting stuff, and maybe it's our hope that the model which I'm going to present can be realized. Leroy, for instance, showed that he was able to produce artificially a diamond chain using atom trap lattices. So this red and blue, it's just a position of some atoms trapped using convenient technology. Here is shown how the profile, what he used, was generated. And it is quite clear that with a little bit more sophisticated technology, he would be able to produce something what we have tried to study. So what we have tried to study is infinite two-dimensional lattice, part of which is shown here. And if you see, it's like set of diamond chain in both horizontal and vertical direction, interconnected to each other. So first model, which I will try to explain, is so-called spin-1 Ising-Heisenberg model. We call it the diamond decorated square lattice because there is some diamond units over there. And this shading shows elementary unit, which consists out of 5 spins enumerated within one unit by indices 1, 2, 3, 4, 5. And ij just denote the position on horizontal and vertical lines of the original square lattice. So with the first model, we consider that corners of the original square lattice is occupied by Ising spins, and on each bond of original square lattice, we are placing couple of Heisenberg spins. What does it mean? The coupling between these spins sitting on blue and red circles, J1, will just contain Z projection between spin operators. So it will be Ising coupling, but the coupling between those two sides, either on horizontal or vertical bonds, will be of Heisenberg type. So J2 coupling is Heisenberg type. And of course, we add also Zeeman term related to the external magnetic field. Just to tell you some surprise, usually, or not usually, Ising model, 2D Ising model in non-zero field is not exactly solvable. But big surprise for us was that at least in some parameter space, we are able to find exact solution for this model. And it shows really unusual behavior. So that's why it might be interesting to study this kind of model. So what I will try to briefly go through the solution. The idea to find the solution of this model is as follows. The total Hamiltonian can be rewritten as or decomposed as a sum of cluster Hamiltonian, so as a sum of such kind of diamond cluster sitting on horizontal and vertical bonds. And this is the definition of such kind of single cluster Hamiltonian. Of course, it contains 4 Ising interaction of 2 Heisenberg spins and its 2 nearest neighbor Ising spins. That's the first term. Then the second term is Heisenberg coupling, which we have between those 2 Heisenberg spins. Zeeman term acting on Heisenberg spin, and of course Zeeman term acting on those Ising spins. There is a factor of 1/4 over there because we symmetrically split this Zeeman term into 4 different diamond cells. So 2 are for this single spin shown here. Another 2 will be this vertical bond and this horizontal bond to the right, which are not drawn. Why this is useful? This is useful that one can easily check that. Okay, let me maybe go back. That the cluster Hamiltonians contain at most 1 common Ising spins, and Ising spins commute with each other. That means that all these cluster Hamiltonian commute, and that's why partition function can be partially factorized into the such kind of cell partition function, each of them corresponding to 1 diamond unit cell, and we can perform trace over degrees of freedom of Heisenberg spins independently of each other. So this is trace over second and third spin from horizontal bond and 4th and 5th spin from the I and J unit cell from the vertical bond. So, and what will be the next idea? Next idea will be to replace this kind of effective Boltzmann weight, which will still, of course, depend on 2 Ising spins, which are involved over there. That's Ising spin with the indices 1. So with some equivalent expression. The idea comes from Fischer. Fischer in 50s, late 50s, shown and that there is some set of algebraic mapping transformation which are known like star triangle and decoration iteration transformation, when you can remove some Ising spin and replace it with some effective coupling and effective field. And the same holds if the Ising spins is coupled to 3 spins and to replace it by effective couplings. And it was already written in his paper, that's the shade sentences, that this kind of transformation may be generalized so as to apply to arbitrary mechanical system coupled to 2 or 3 spins of basic Ising net. So he never applied to some quantum spins, but already in his paper was this idea. The idea that if you have any decorating system, you can trace out degrees of freedom if it's coupled to 2 Ising spins, and you can replace by the effective coupling and effective fields acting on these corner Ising spins. And that's what mathematically is written by this transformation, containing some multiplicative factor A, effective interaction R11, and effective field R10, R01 acting on the left and right spin. And by simply placing all 4 possible combinations of Ising spins, you will get 4 algebraic equations, which you can, of course, solve. And these 4 algebraic equations determine unambiguously through the self-consistency condition all 4 unknown mapping parameters, and they will be expressed in terms of Boltzmann weight for a particular configuration of Ising spins. So this idea was elaborated by Onofre and his colleagues and myself roughly 10 years ago. So if we apply right now these 2 diamond decorated square lattice, what we will do, we will replace this diamond cluster by just two Ising spins coupled by effective coupling and effective field. Since we have left-right symmetry, effective field will be the same as I will show later on. And the same holds for vertical bond. So that means that after performing this trace, and trace over degrees of freedom means just to work in subspace, parameter subspace of 4 states of 2 Heisenberg spins. So that means that we can simply diagonalize this Hamiltonian in this subspace. Trace is invariant with respect to transformation. And if you find those 4 eigenvalues and they sum up them, so we will get this expression. So that's the effective Boltzmann weight, which already doesn't depend on degrees of freedom of Heisenberg spins. And as you see here and here, it depends just on 2 outer Ising spins. And we use this Fisher idea on the right-hand side. We will put this kind of decoration, iteration, transformation. So plugging in over there all 4 possible combinations of 2 Ising spins, up, up, will lead to first equation, down, down to the second. And if we have up, down, or down, up, there is a symmetry. There is a plus between them, also over there on the right-hand side. So there will be just a single equation. That's why we don't have 4 equations, just 3. And we see that we are getting like 3 different Boltzmann weights. And just simply solving this set of 3 algebraic equations about 3 unknown parameters, multiplicative factor A, effective coupling JF, and effective field HF, we are getting this kind of solution for all 3 unknown mapping parameters. And now, this kind of solution, this kind of transformation, if we know already these mapping parameters, can be substituted back to the factorized form of the partition function. And what we will achieve, we will get some mapping relation between partition function of spin-1/2 Ising-Heisenberg model on the diamond decorated lattice and simple spin-1/2 Ising model with effective coupling and effective field. So that's really great because we mapped semi-classical, semi-quantum system onto purely classical model, which can be solved, of course, more easily. Moreover, it's important that Ising model is exactly solvable in case the effective field is 0. What does it mean? We can simply put here effective field equal to 0, and then we will get parameter subspace where we even have exact solution. And the exact solution will be given by solving this transcendent equation with respect to true field. Effective field is 0, and this equation will determine for a given couplings J1, J2, the value of the true field when the effective field is 0 and when the system is mapped to the exactly solvable subspace. And moreover, if we satisfy this condition and the effective temperature equals to the critical temperature, what was found by Onsager, we can get also critical points of course, of Ising universality class, and the condition of this critical temperature is shown here explicitly. So we found exact solution even in non-zero field, and we are able to study phase transition in non-zero magnetic field. Before showing this result, let me just to better comprehension, first to show phase diagram. Phase diagram of Ising-Heisenberg model can be found very easily because that whole system can be written as a sum of cluster Hamiltonians, commuting cluster Hamiltonians. Each of them we have diagonalized, and we can get eigenfunction and eigenenergies for a given clusters, and from that we can build out all possible ground states. So the first ground state, which appears at low fields and low values of interaction ratio J2 over J1, is classical ferrimagnetic state when Heisenberg spin point out and the Ising spin point down. Then if we are still at low enough field but higher values of the ratio, So we are getting singlet state. So this ellipsis means singlet dimer state on both horizontal and vertical bonds. That's these eigenvectors. And all Ising spins, because singlet decouples all couplings J1, so they are completely free. So in zero field, they can point up or down. So in zero field, this monomer dimer state is infinitely large degenerate with a degeneracy factor 2 to the power of number of Ising spins. But arbitrary non-zero field will polarize them up, as is shown here for arbitrary non-zero field in this eigenvector. The second corresponds to this classical state, ferrimagnetic. And of course, if the field is large enough, we are getting saturated paramagnetic state, which is given by this state that all spin points are. So what we have done, these phase boundaries are shown by green line, and here you can see there is something else. It's some broken line, and this is a projection of our solution of this critical condition which I showed you here. Projection, if you solve it, and if you make projection to the zero temperature plane in this parameter space, it closely follows this line. It is not exactly the same. One cannot see it so well. So that means that this critical line with very high probability transition between ferrimagnetic and monomer dimer state. And I have very strong argument that must be like that, because what we know, along this critical line, we have zero effective field. And zero effective field means that on Ising spins can be either up or down. We have to have both solutions, because both solutions are equivalent if the effective field is zero. And you see that in both states, we have a difference of Ising spins orientation. So to understand better what happened, let us show how the effective coupling and effective field behaves in the limit of zero temperature in the same plane. So the first figure, this panel A, shows in the same plane J2 over J1 with respect to field, effective coupling in multipliers of coupling J1, and one can see that it is non-zero just within this stripe. So whenever field is greater than the sum of J2 and J1, or is smaller than the difference J2 and J1, effective coupling is zero. So we have non-zero coupling at zero temperature just within this stripe. If you look on effective field, so once again normalized with or in multipliers of coupling J1 in the same plane, you see that the effective field even changes its sign. So white color corresponds to zero, and you see that there is a white color over there when the true field equals to 4, and another white is when it starts from 1 and goes linearly up to the value of 4 with this tangent, and the blue area means zero, negative effective field, and red means positive one. And now if we plot phase boundaries, these are these green broken lines which are not well seen, one can see one important thing. One can see that the line, first order phase transition line between ferrimagnetic state and saturated paramagnetic state run through the region where the effective coupling is zero. It is zero. That means we cannot have phase transition, we cannot have spontaneous ordering if we don't have coupling. If you look on the phase boundary between saturated paramagnetic state and monomer dimer state, it is exactly boundary when still effective coupling becomes zero. So also along this phase boundary between monomer dimer and saturated paramagnetic state, we don't have coupling. And the only phase boundary which runs through this stripe with non-zero effective coupling is the one between ferrimagnetic state and monomer dimer state. And to have phase transition, to have spontaneous ordering, we need to have, for spontaneous ordering, non-zero effective field. And if we want to have phase transition, we have to have zero effective field. So that's exactly what we have, because along this line, we have this kind of zero effective field. So this is already indirect proof what I told that this solution, mathematical solution, corresponds to the phase transition between ferrimagnetic state and monomer dimer state. So here is a 3D plot, how it looks like the solution of this phase boundary between ferrimagnetic and monomer dimer state in the plane field versus interaction ratio, and on z-axis is a temperature. And this is a blue dotted line, which is over there. And the area which is going from 0, this green line, which is the phase boundary, ground state phase boundary, first order type between ferrimagnetic and monomer dimer state. And the area delimited by this first order phase boundary and the second order phase boundary corresponds to the 0 field. And this is shown for few values by red, almost vertical lines, first order lines. I will just show it that they are not perfectly vertical in a moment. The other figure, because 3D figures sometimes it's hard to understand, shows the deviation of this critical field, which corresponds to this blue line, from the one which corresponds for a given interaction ratio at the 0 temperature. So you see that indeed, if we have interaction ratio from 1 to 2, so some up to the middle and the highest point of this critical line, we have movement to the left to the smaller values of the field, and then at 2 we have greater. So it seems like sinusoid behavior in the projection or in this 0 temperature plane. Maybe it's also hard to see, so maybe it's better just to show it on some few cuts. So if we look and we will fix the interaction ratio less than 2, so what we see, the red line is showing this 0 field, 0 effective field phase boundary between ferrimagnetic phase and monomer dimer state, and this phase boundary is terminating at Ising critical point when we have when we reach also the value of the critical coupling ratio shown by an Onsager. And if we increase this interaction ratio, it just moves up. And something interesting appears, of course, around 2. So if it's greater than 2, you see that the bending is on opposite side of this first order phase transition line. So already at 2, it starts to be bent on the side of ferrimagnetic phase and not monomer dimer. And if you are slightly below 2, that's the most interesting parameter space, because we can have even first bending on the side of monomer dimer state and then bending back to the ferrimagnetic state. And now you could imagine if I would fix field somewhere here and increase temperature, I can have a reentrance phase transition with 2 reentrance, first order reentrance phase transition. All the results are exact. So one can conclude what is written here. So if the interaction ratio is less than 2, we have monomer dimer state on the low temperature side, ferrimagnetic state on high temperature side. If it's greater than 2, reverse is true. And if we are slightly below 2, we can have also double reentrant phase transition from monomer dimer state to ferrimagnetic and back to monomer dimer state. To understand why, from where the reentrance comes, so it is, one can easily elaborate the free energy for both states. We have the eigenstate, and we can take the lowest energy excitation, and this is a density plot of this lowest energy excitation above. Here is ferrimagnetic state, and here is monomer dimer state. And what one can see that if we are below 2, so here is more light color on the side of ferrimagnetic state. What does it mean? It has a lower energy gap. And if it's lower energy gap, it can gain higher entropy. And that's why the bending is on the side that ferrimagnetic state appears at higher temperature. So bending must be on the side of monomer dimer state. But if you are above 2, the reverse is true. Now the energy gap within monomer dimer state will be will be smaller, and that's why the bending will be on the right. To understand reentrance, we need to add not only lowest energy excitation, but also the second excited state. And our arguments just take into account this kind of expansion, including first or lowest energy excitation, are shown on this figure by this blue broken line. So my argumentation is perfectly correct. And that means that we are even able to understand and to explain microscopically the nature of reentrance phase transition and why the first order line bends for some parameter space to the left and why the first order phase transition line bends to the right on the parameter space greater for the interaction ratio greater than 2. Okay, this is interesting, but you would say, okay, we would like to see some independent proof. So let me take this coupling ratio and let me take a few field dependencies of some typical quantities when changing, when fixing temperature and going along those 4 temperatures, well below critical temperature, slightly below, then almost exactly at critical temperature and above it. So this is simulation of effective Ising model from which classical Monte Carlo simulation for lattice 120 times 120 and with a lot of Monte Carlo steps. So there is almost no error bars, or error bars are smaller than the thickness of those lines. And if you see that if you are at very low temperatures, we indeed see this phase transition. So I was really surprised that Monte Carlo was so impressively in accordance what we found analytically through this solution. So the green broken lines just show Ising magnetization, and you see that it is almost polarized at low enough temperature, and it jumps then in opposite to the field, and that corresponds to monomer dimer state, and this ferrimagnetic state. Indeed, dotted blue line is magnetization of Heisenberg spins, and that means that we have zero magnetization because we have all singlets, and then it jumps to saturated value. And here we have this first order phase transition line, which was nicely reproduced by Monte Carlo simulation. And the red line, of course, shows the total magnetization. And you also see that there is no phase transition, and there is just simple crossover from ferrimagnetic state to fully saturated state, in agreement what I showed you before, that the effective coupling is zero. If you increase temperature, jumps diminishes, all dependencies become smoother. This is very close to the phase transition, but slightly below, so one can still see some smaller jump. It should be perfect tangent with infinite tangents over there, with the susceptibility having this critical exponent 7/4. And if you are at high enough temperature, you see that already the tangent is finite, and you have smooth dependence without any phase transition. So if I would now just remember that I make these 4 cuts and all 4 magnetization, just total magnetization would be plotted, you have seen this nice picture, low enough temperature, almost perfect jump, increasing temperature, decreasing size of the jump, and high enough temperature, just smooth dependence without any phase transition. Here is the dependence of susceptibility, and susceptibility shows something, indication of divergence close to this critical temperature. Unfortunately, our data were not precise enough to get critical exponent just to show that it's exactly 7/4 over there. And the question would be, what is the order parameter for this phase transition? So order parameter is shown in this right up panel, and it is density of singlets. So in one state we have singlets, in the other state we have polarized triplet, and you really see that all dimers are at low enough temperature in singlets, and then it almost jumped to zero. So this is discontinuous phase transition. And if you increase temperature, this dependence just becomes smoother. Of course, there are still jumps. If temperature is below critical temperature, and if it's above, it just shows this crossover from a large singlet number of decorating Heisenberg dimers and small ones over there. Okay, just to show also reentrance, So we also make cuts in the parameter space when the interaction ratio was just slightly less than 2, and fixing field to 4 different values below when we don't have phase transition, when we have 2 first order phase transition, just one of them, and when we have second order phase transition. So indeed, you see here is just simple crossover. So if we change the temperature, no phase transition is seen if we are over there. If we tune the parameter space to have double reentrance phase transition, we can see 2 jumps from Monte Carlo simulation. They are in perfect agreement with the phase diagram which we elaborate analytically. And then, of course, smoother dependence at higher temperatures. Even changing the field to higher value, there is just 1 first order phase transition, and that should be pretty close to the second order phase transition, when it should be quite smooth. This is once again summary of all those results, including order parameters, that you can see that we have almost just singlet state up to this temperature. Then all dimmers, Heisenberg dimmers on decorating sites, come to polarized triplet state. Then number of singlets start to rise with the increasing temperature because of thermal population, and then it almost jumps back. So you can see also reentrance from this order parameter. You can see just red curve is below, this is without phase transition, or just with a single phase transition, this is this green line, and second order phase transition should be that one, these orange lines. And here is the, once again, picture of the total magnetization. And just to show you also specific heat, we can see first order phase transition like finite peaks in specific heat. And when we are pretty close to second order phase transition, this is this orange line. It is very reminiscent of logarithmical divergence. Once again, we were not able to perfectly prove logarithmical divergence. Well, second part of my talk will be focused on Heisenberg model. And so it is the same model, just all coupling isotropic Heisenberg ones. So I will probably not need to explain. So it is completely the same, but now all spin are Heisenberg, of Heisenberg type. And let me just tell you something more about that. So, of course, this is much more difficult problem. One cannot factorize to some local commuting Hamiltonians and to use the procedure as it was used before. But what one can understand, if we sum up total spins on, let's say, horizontal and vertical diamond cells, we are getting some spin operators which commute with the Hamiltonian, and the Hamiltonian can be rewritten also in terms of these composite spins, composite for these decorating Heisenberg dimers. And if we sum up 2 spins, we know that the total spin can be either 0 or 1, either singlet or triplet state. That's those 4 states. So what does it mean? This Hamiltonian, or the equivalent representation, is given through these composite spin values, and this corresponds to so-called Lieb lattice. So, of course, this original Hamiltonian is hard to solve. We can try to make full exact diagonalization, Lanczos technique for original Hamiltonian, but all of them will be restricted to relatively small system sizes. But the other point is that if we use this correspondence, we can make simulation of the effective model, and at 0 temperature, the best would be DMRG, because we can proceed to very large system sizes. And you see here what Andreas was speaking about in his talk, on the first talk of this workshop, that if we are able to write the Hamiltonian in this form, we get rid of these kind of triangles, we get rid of spin frustration in the effective language, and that's why in a proper basis, by changing standard basis of SZ component of the spins to dimmer basis, because this side is nothing else like eigenstate of 2 spins, we'll get rid of sign problem in quantum Monte Carlo simulation. So we can perform at finite temperature quantum Monte Carlo simulation in the dimmer basis. In that case, it will be without sign problem in whole parameter space, and that's really great. So first, let me show you the result for zero temperature. So red broken line show the result for exact diagonalization of the lattice size with linear size 2. That means 4 unit cells, 20 spins. And the blue line is for this effective model with how many? See, 6 linear size. So that's 36 unit cells times 5, so 180 spins it corresponds. So one can see that if the interaction ratio is small enough, we have Lieb-Matisse ferrimagnetic state. The numbers in the bracket determine the total spins on horizontal and vertical dimers is 1. So this is nothing else like bipartite lattice for which Lieb-Matisse theorem applies, and that's why we know that it should be like that. So it is this 3/5 plateau, which has a gap, and the gap closes with increasing field, and then we have like quantum spin liquid state when magnetization continuously rises. Both methods give perfectly results which are in good accordance if you consider finite size analysis. If you increase the interaction ratio, one finds also zero plateau. Greater increase of the interaction ratio, there appears another 1/5 plateau, and over there all composite spins are zeros, they are singlets. So this is nothing else like what we found in Ising-Heisenberg model, that's monomer dimer state. Further increase of the interaction ratio, zero plateau diminishes, and once again further increase of the interaction ratio, also this ferrimagnetic Lieb-Matisse ferrimagnet diminishes, and finally at highest value we have just 1/5 plateau. So using this kind of result, we were able to elaborate ground state phase diagrams, and this contains those phases. So saturated paramagnetic state is the same as I was speaking before. Monomer dimer state exactly the same, including the same eigenvector, it's schematically shown here. Lieb-Matisse ferrimagnetic state, we have triplets on all decorating dimers, and Ising spin before. Now Heisenberg spins, they have just smaller quantum reduction of magnetization, but the nature of the state is the same. And we have spin liquid state, which is separated by 2 horizontal lines, which are second order quantum phase transition. All the other lines are first order quantum phase transition line. And the most interesting behavior concerns dimer tetramer state, where we have singlets on these diamond plaquettes, and the condition is that these singlets on diamond plaquettes are surrounded by 6 singlets on dimers. And there is a hardcore repulsion. We cannot place closer those singlets. And this state is macroscopically degenerate, because if I will move it up or make it horizontal one, I can elaborate infinitely large number of states. And this is the zero temperature phase diagram, including the numbers between those 3 states. So how I can elaborate something at finite temperature? So if I consider the parameter space greater than 4, I am in this space when I have just monomer dimer state and saturated paramagnetic state, then I can realize that these monomeric sides, blue ones, are always polarized, and the decorating dimers are either singlets or polarized triplet state. So what if I would try to make some particle representation of that state? If there is a singlet, let's put particle, and if there is no singlet, polarized triplet, let's be empty. And these sides will be always polarized. And what does it mean? I can write effective Hamiltonian starting from fully saturated paramagnetic state, that's its energy. This is Zeeman term for these spins. And then this will be just chemical potential. What is the difference of singlet and polarized triplet state, whether this bond is in singlet or polarized triplet state, and this is occupation number. And this is lattice gas of non-interacting hardcore monomers, independent, and that's why it's easy to elaborate. One can find free energy. And this is a picture which shows these highest values of the interaction ratio, that you have just 1/5 plateau, and the symbols show exact diagonalization for 20 spins for unit cell, and the lines running through the, so that's why you don't see anything, because it's perfect agreement. So line running through these symbols just show that it is perfect. So this was just for this most easy parameter space where we can elaborate and we can describe magnetization, specific heat, whatever we want. So this lattice gas representation is really useful. Of course, most boring. But why we have done that? Because now we can compare lattice gas approach, exact diagonalization, and also quantum Monte Carlo in dimmer basis. So this is the basis. And just to show that quantum Monte Carlo is perfectly works well. So that means that we can trust, if it works here, it will work in whole parameter space. There is no sign problem anywhere. And we can elaborate also, and what was the most for us puzzling or interesting, along the line where we found for Ising-Heisenberg model, first order phase transitions terminated at the Ising critical point. Can we see this in full Heisenberg model? So the answer is yes. So this is the density plot of specific heat from the quantum Monte Carlo simulation in the plane interaction ratio versus temperature for two fixed values of the field, 2 and 2.5. They are running exactly through this phase boundary between Lieb-Lattice ferrimagnetic state and monomer dimer. And you can pretty see that there is some very intense peak in specific heat. And one can even see that the bending for lower values of the field is to the right and bending is to the left. So it's completely the same physics as I explained in Ising-Heisenberg model. So it is very useful from that point of view. And moreover, here is a scaling analysis of dimmer susceptibility. So susceptibility of density of singlets. And you see that with increasing system sizes, one can have a divergent, and even the divergent for dimmer susceptibility has a power law exponent 7/4. It is for Ising critical point. There are just 2 points, but probably you can trust me that it should be fine. So this first order line indeed terminates at Ising critical point. So Heisenberg model shows the same physics along this phase boundary between Lieb-Lattice ferrimagnet and monomer dimer state. Okay, there are a lot of another phase boundaries. This one is between if we fix the field 4.5, so we are running through spin liquids to monomer dimer state, and if you create density plot, the situation would be different. Our colleagues from Aachen found out that the phase transition is of Kosterlitz-Thales type. You see that the critical points, these green points, are almost at the border to which low temperature they can go. They still continue their efforts to go slightly below just to be more convincing, but they found also this spin stiffness and its behavior 2/pi times t. And from that, they conclude that this is Kosterlitz-Thales type phase transition. So over there at finite temperature, it's like that. Okay, so let me gradually come to the conclusion. So let me tell you most interesting results, what we found. We found that we can solve 2D model, Ising-Heisenberg model in non-zero field in some subspace, but this subspace is the most interesting because it shows first order or second order phase transition, and we have exact analytical results for this. These results were independently confirmed by classical Monte Carlo simulations, and what was most interesting from my point of view, we were able microscopically to explain double reentrant phase transition from monomer dimer state to ferrimagnetic state and back to monomer dimer state. Heisenberg model on the same lattice shows a pretty similar behavior concerning transition between ferrimagnetic and monomer dimer state, including the bending of the first order line to the left, to the right. We are able to understand it. Also, it shows some new states and much more diverse quantum phase transition, maybe also classical one. So it is quite interesting to study. And for this highly frustrated parameter vision, we are able to elaborate analytical technique, analytical lattice gas model of hardcore monomers, which can explain the physics. What we still have to be done, this is still unfinished work, unpublished. So there are a lot of other stuff. For instance, dimer tetramer phase, which is macroscopically degenerate, its phase boundary is big challenge. We think that we are able to map it to model of hard dimers on square lattice and to study it from that. But at the phase boundary, there will be a lattice gas model of hard monomers and dimer, which is not anymore fully exactly solvable model. And the system will probably show really intriguing temperature-driven and field-driven quantum phase transition, what we would like to study in the future. So my last slides is acknowledgement. First, let me thank my collaborators, which are shown in all these pictures, which without which this work couldn't be done. Let me thank Marcelo, Jordana, Luan, and Socorro for the kind invitation and for this workshop. It's 6th time for me here in Maceo, and I always enjoyed very much. Let me also thank Slovak grant agencies for supporting our research. And this is just an announcement that next year we will have 2 conferences in Slovakia. One of them we will directly organize it's here, in High Tatras, our highest mountains. It's a picture from which you can see. And this is a hotel where it will be located. This is lecture room. So it will be in May 23rd and 25th. I will be really like to invite you. I will try my best to help you to maybe without fee and maybe also trying to get for you free of charge accommodation in case you would be able. Unfortunately, we are not able to cover your expenses for travel. And the other options is at the end of June 2023, it will be conference on magnetism directly in our city. We are not main organizer, but we are very close to main organizer. So it will be also nice if you are working in magnetism and you find this like interesting to come. So thank you very much for your attention.
Okay, so thank you, Jozef, for the very interesting talk. Let me ask if we have any questions from the audience here first. Marcelo?
It's really surprising that the Monte Carlo results for the Ising-Heisenberg model is consistently the result of the transfer matrices, the decoration transformation, considering that the effective field is 0. It means that all transitions that we can have in this model are transitions on which the effective field is 0. Is that a possibility to have a transition on which the effective field is not 0 in the nodal sites?
We come here, and the answer is no. And the reason is very simple. If you look, effective coupling is always greater than 0. Effective coupling is always ferromagnetic. And once we have ferromagnetic coupling, effective coupling, so you cannot have a non-zero effective field and non-zero ferromagnetic coupling phase transition. Ferromagnets cannot have it. If the effective coupling would be of opposite sign, or it would change the sign, it could happen, because it could be phase transition like anti-ferromagnet or metamagnet, ferrimagnet show. But this never happens in this special model. We check an effective coupling. You see on this density plot, of course, just for 0 temperature, but we check also for non-zero temperature. It is always greater than 0. So it is never negative, and that's why I can pretty honestly answer that this kind of phase transition cannot appear, at least in this model.
Okay, do you have any more questions from the audience? One? Oh, yeah. There's a question. You can go ahead.
Okay, so thank you, Jozef, you have always good presentations. Concern the full Heisenberg model, I think when you run the distributions, you cannot reach the two-dimensional model because it's a hard Hamiltonian to simulate, etc. That phase that you call diagonal has a macroscopic degeneracy.
Yeah.
So in That's some 2D spin liquid phase who can be described by the resonance response solid picture. And my question is maybe this describing of the 2D spin liquid phase maybe can be applied from this phase or to two-dimensional phase, or you think
I don't think so. I don't think so. And maybe I will try to explain you why it's not like that. It's simpler. It's much more simpler. The nature of this state is much more simpler because just forget in this picture all decorating atoms and just have a look on the ovals which delimit these tetramers. That's singlet tetramers. And if you see, and if you will try just to put some bond on that. And now let's put also bond on that and bond on that. So this is nothing else like putting hard dimer bonds on square lattice. And we make the calculation of residual entropy for small system sizes analytically, first by hand, just simply for small, like 2 by 2, you can write it by hand, 3 by 3 as well. And then we also checked with the residual entropy from exact diagonalization and the other technique, and it was in perfect agreement. So even what I can honestly say about this state, I know exact value of its ground state degeneracy because it corresponds to the model which was solved by Lieb, and it is hard dimer model on square lattice. And this is known exactly. And why it's not this kind of resonating? Because singlet dimers, which are surrounding each singlet tetramer, break all the correlation. So that means it is really like some liquid composed of two kind of singlets, and there is just hardcore repulsion between these bigger singlet tetramers, but they are not really resonating. There is no this kind of tunneling term which would correspond to this state. So that's the other type of quantum spin liquid what you mentioned. That's different mechanism.
Thank you. Okay, so let's see if we have questions from online participants.
Also, they have a question.
Yeah.
Yes. Azadeh, please, you mute your microphone or send your
yes.
question. Okay.
Hello.
Hello.
Excuse me. Thank you very much for the presentation. My question is that if we can solve the Ising-Heisenberg two-dimensional model without using the decoration iteration method. You know, you wrote the if we just write the density matrix, if we write the transfer matrix and without using the decoration iteration method. Is it possible?
Yeah, the answer is yes, but the results will be the same. So in fact, what you will need to do, you will still write the density matrix for such kind of cluster, and you first need to trace out degrees of freedom of quantum spins. And finally, you are able to write the transfer matrix. So you will avoid, in that case, decoration iteration transformation. But finally, what you will get, it will be completely equivalent representation. And since it is easier just to take an exact result, which was found by Onsager, so I would say this is a shortcut to the exact solution.
Yes.
But you are right, it is possible just simply by transfer matrix. So first, the result would be first to trace out degrees of freedom of Heisenberg, all Heisenberg dimers on decorating sides. And then what you will get is something what you can treat simply by transfer matrix approach, but in the same tour de force how Onsager has done it. So it's not so simple. So it's better to use Onsager's solution and to make shortcut directly to his final result.
Thank you very much.
You are welcome.
Okay, Do you have any more questions from our online participants? Or from here? If not, let's thank Jozef again. And we have a break now. We'll be back in about 15 minutes for 2 more talks.